So the latter half of 4.5 is all about solving logarithmic equations. Now, it's a very simple section, so we only really have one lesson goal, and that is to solve any logarithmic equation I give you. Now, the last lesson yesterday, we talked about how to solve exponential equations, and the main logic, even though I sort of had like 4 problem types, the main logic was if your variable that you're solving for is hiding up in the exponent, you might have to use a log to bring them down, because that's the power of a log. That's the job of a log, is to bring down exponents, because exponential functions and logarithmic functions are inverses of each other. So today it should make sense that for today we're just going to flip the logic. To solve logarithmic functions, all we're going to have to do is use exponential functions, exponential bases. Just like with yesterday, I'm going to try to categorize or group these problem types into, well, types. And just like with exponential equations, I sort of have 4 subcategories. So let's talk about each of them. Starting with the easiest one, type 1. These equations will look like log equals log, but they will have the same base. Now the logic will be nearly identical to the type 1 equations of yesterday. The logic is, an equal sign is very powerful. If we have a logarithmic expression, say log base b of x, and I claim that it equals another logarithmic expression, log base b of y, well, if log b equals log b, then the only thing that we can deduce or we can conclude is that the arguments x must equal the argument y. If yellow equals yellow, then pink must equal pink. So that's sort of the idea. So let's do a quick example here. Suppose I ask you to solve log base 6 of 2x plus 8 equals log base 6 of negative 3x minus 2. So notice, hey, log base 6 equals log base 6. So what can we conclude? We conclude that the arguments must equal to each other. So this is 2x plus 8 equals negative 3x minus 2. Then from this point on, it's just simple algebra. All right, get all the x's on one side, get all the non-x's on the other. So we'll go ahead and add the 3x over, and at the same time subtract the 8's. So we get 5x equals negative 10. Divide out the 5, x equals negative 2. Now actually I don't want to stop here. I sort of want to make a comment. Yesterday when we were solving exponential equations, when we did our math, when we got our answer, that was it. Boom, you're done. But we were sort of taking an idea for granted. We took the idea that the domain of the exponential function is always all real numbers for granted. That meant that if you trusted your math, which I'm pretty sure we can, whatever answer you get is whatever answer you get. It's totally fine. It's legitimate because basically any x value will work for exponential functions. Not true for logarithmic functions. Remember back in, I think it was 4.3b, we were sketching and finding the domains of logs. We saw that logarithmic functions have domain restrictions. Specifically, little warning, recall that the domain of any log base b of x, let's write that as a function here. I'll write that as an equation. Y equals log base b of x is that the input or the argument has to be greater than or equal to 0. What does this mean? What is the implication for us in terms of solving? This means we must check all answers to log equations. So this is something that we skipped when we did exponentials because we really didn't have to. Honestly, for log equations, we sort of have to check our answers. But what is it that we're checking against? We just do not want a negative or a 0 inside of a log. So let's go ahead and check our answer here, right? So I'm going to check x equals negative 2. And all you need to do is check it within the arguments. That's it. I don't really need to see, if you trust your math, I don't need to do all simplifying, plugging it in, making sure the left equals right, although in this case it's pretty simple because we only have one term. You just want to see if whether or not the argument is positive. So let's check x equals -2 into the first argument. So you have 2, -2 plus 8. That equals a 4, which is a good number. It's not 0, it's not negative. And let's go ahead and check the other argument, -3, -2 minus 2, which is 4, as expected. Right. So in this case, x equals -2 is a good answer. There may be instances, there may be examples where you might have to throw away one or sometimes both answers. Let's just do a quick example, another example, showcasing this exclusion. So let's go ahead and solve log base 15 of x plus 2 equals log base 15 of x squared minus 10. Again, hey, the logs are the same, so I can use an implication to say that the arguments are the same. Oh no, this is a quadratic equation, so I can't just simply solve for x. The techniques to solve for a quadratic is you want 0 on one side. So let's go ahead and subtract the x and subtract the 2 over. That gives us x squared minus x minus 10. And gee whiz, it's as if whoever picked this example wanted to make sure that it factored nicely to make it easy. And indeed, this guy is factorable nicely. I think it's a -4 and a +3. So that gives us x equals 4, x equals -3. But we must check our answers. We have to check against the arguments. So let's go ahead and check x equals 4. So we have 4 plus 2. Well, that's 6, so we're good to go there. Let's check the other argument. 4 squared minus 10, so that's 16 minus 10, which is 6. That's good there. Let's go ahead and check x equals -3. So that gives us, let's check the first argument. -3 plus 2 equals negative. Oh, this is a problem now. I can't have a negative inside of a log. This is bad. So I don't even have to bother checking the other argument, the pink argument. The moment that one answer does not work, you can just throw them out. So this is a bad answer. We only have one solution, x equals 4. So that's all that warning is about. Just make sure that you check your answers. Right. So easy peasy, I hope. Let's move on to the next type of examples you might see, type 2. These are problems with more than 2 logs, so a lot of logs, but no constants. So you have logs everywhere, but you don't have any loose numbers by itself. This is the idea. These types of problems, since they're just nothing but logs, they are sort of the generalized form of type 1 because we have these things called properties. So the strategy or the idea is to use properties of logs to condense each side of the equal sign and turn the problem into a type 1 problem. And this is sort of why we talked about properties of logs, because it allows us to do stuff like this. Let's take a look at an example here. Suppose I ask you to solve log base 5 of x plus log base 5 of x plus 1 equals log base 5 of 20. Good gosh, there's logs everywhere. But notice that all the numbers, all the stuff are inside of a log. We don't have like an extra +3 floating around, so this is good. So if you have logs everywhere, the idea is just to use properties. Well, you have to know your properties. So turn back to, I think it was 4.4. We made a list. There's only 3 of them. The product property, the quotient property, and the power property. So you must know those. Well, the only place I can apply the property is right here. I have two logs adding to each other, and the property says when you have two logs adding to each other of the same base, you can condense them down as long as you multiply the arguments. Now notice this is a type 1 problem now. You have log equals log. Well, if the bases are the same, then the arguments must be the same. So I can logically deduce that, and I'm going to go ahead and distribute at the same time. We can logically deduce that x squared plus x is equal to 20. And what do you know? We have another quadratic that hopefully is easily factorable. Again, if it wasn't factorable, you can always use the quadratic formula. So this is x plus 5, x minus 4. So that gives us x equals negative 5 and x equals 4. But again, you always have to check against the original, you have to check your answers, and you need to check against the original format of the equation. So we need to check against this argument, and we really don't need to check against this argument because he's a solid 20. So let's go ahead and check negative 5. Check x equals negative 5. Let's check against the yellow arguments. Well, no, that's easy. If I plug in a negative 5, I get a negative 5. This is bad because he's negative. So I don't have to go any further. I can cross this guy out. Let's check x equals 4. Well, for the yellow, that's pretty easy because you're just plugging in a 4, so that's good. What about the red? So if we have 4 plus 1 that equals 5, that is not negative or 0, so that's good. So x equals 4 is a good answer. Okay. So let's just do one more, just because I don't know, I like to do examples in pairs. Suppose I ask you to solve log base 4 of x plus 2 plus log base 4 of 3 equaling log base 4 of 5 plus log base 4 of 2x minus 3. This may look like a scary problem, and indeed it is pretty lengthy, but just check what you have. This is a log, this is a log, this is a log, this is a log. Everything is a log. There's no loose separate constants, so the name of the game is to transform it into type 1 by using properties. Everything is plusing each other, so according to the product property, you just multiply everything together. So this is log base 4 of 3 times x plus 2. That equals log base 4 of 5 times 2x minus 3. Since the logs are the same, the arguments must be the same, so we can use a logical conclusion. And I'm going to go ahead and distribute at the same time. So we should know that 3x plus 6 is equal to 10x minus 15. And then in this case, it's a simple linear equation that you can then just solve for x. So let's subtract the 3x over and add the 15. So we get 21 equals 7x. So x equals 3. And then, of course, you must check against the arguments. I hope you guys get the idea by now. I'm going to sort of be lazy and fast forward through it. I'm just going to say it out loud instead of writing it out. But if you were to plug in x equals 3, if you were to check against the arguments, this is a good answer. So the third type of log problem you might face is when you have a log equaling a number, right? So this is where we actually start using an exponential function. This is where we can't really use logic to deduce. So the idea or strategy is that since exponentials and logs are inverses of each other, we're going to use an exponential base. So to get rid of a log function, you will exponentiate, that's a fancy word, both sides of the equation to the same base as the log. So this word here, exponentiate, that means to transform into an exponent. So you're basically going to take the equation, which should consist of regular terms on ground level, and you're going to push them up into the exponents on top of a base that matches the log. I think this will make a lot more sense when you guys see an example. So let's take a look at an example here. Suppose I ask you to solve log base 2 of 25 minus x equaling 3. So this is a log equals a number problem. So what you're going to do is, since I see that I have a base 2 here for the log, we're going to exponentiate both sides of the equation to base 2. So I'm going to start with the regular base 2, and then this log base 2 of 25 minus x, he becomes an exponent. Notice how I pushed them up into the exponent. Well, of course, what you do to one side, you got to do to the other side. So I'm going to push the right-hand side up into the exponent. This is called exponentiation. So, of course, base 2, they quasi-cancel out, leaving us with 25 minus x equals, and then this should just be a regular number you figure out. 2 cubed is 8, and voila, we have a regular linear equation to solve. So solve for x really quickly, you're going to get 17. This is a log problem, so you must check your answer against the argument. Let me tell you, when you plug it in, it's going to be a good answer. Just like with exponents, though, the exponential equations, you know how yesterday I said, hey, wait a minute, you don't want to use a log until the exponential is by itself. It's the same idea here. You do not want to exponentiate until the log term is isolated. Right? You cannot, or you should not, exponentiate until the guy that's carrying the x is by itself. So for example, if I ask you to solve 4 plus 3 log of 2x equals 16, what you should be thinking as a student is, okay, I'm solving for x. Where's the x? X is right here. Oh, I notice x is attached with the 2. And I notice that this 2 is the argument of a log. So anything that I did not highlight, I need to get rid of. That is the thought process. That is the thinking that we should be doing. And hopefully we can see that in this case, we need to get rid of the 4 and we need to get rid of the 3. So let's just, that should be just regular algebra. So the first thing we're going to do is get rid of the 4 via subtraction. That leaves us with 3 log of 2x equals 12. And then we're going to get rid of the 3 via division. And that gives us log of 2x equals 4. Now we can go ahead and solve this guy. So we're going to exponentiate. Now this is a common log because we don't see a base. So we're going to exponentiate both sides with base 10 because common logs is always 10. The left-hand side, they quasi-cancel out, giving us 2x equals, and then this is just a number you figure out. 10 to the 4th is 4 zeros, so that's 10,000. And then the last step is to divide both sides by 2. So 5,000 is your answer. But of course, you got to check your answer. So here's the original problem. You have to check against the arguments. That is definitely not going to be 0 or negative. So this is a good answer. So last but not least, the fourth type. And honestly, it's just like type 2, where type 2 was a generalization of type 1. This here will be a generalization of type 3. It's basically the more, quote, complicated version. What if you have lots of logs and constants? Right? What if you have lots of logs floating together and regular numbers? Well, in type 3, in type 2, the idea was, hey guys, we're going to change this into a type 1 problem by using properties of logs. Guess what? It's going to be the same idea. The idea for this guy is use properties of logs to change the problem into a type 3. So basically, if you can solve a type 1 and a type 3 problem, you can solve all the log equations you want. Well, before I can use properties of logs, you sort of want to gather all the logs together. So implicitly, even though I didn't say it, properties of logs only work with logs. So if you had logs on both sides of the equal sign, you'd probably want to carry them over to both sides. So this is what I mean. Let's take a look at this example. Suppose I ask you to solve log of x plus 2 equals 1 minus log of x minus 1, right? Hopefully we can see, oh, I got logs here, and I have regular numbers. So this is a bad thing. That's sort of like a monkey wrench. So the idea is, okay, I'm going to gather all the logs together. So the first thing I'm going to do is I'm going to move this guy to the left. I'm going to add log of x minus 1. So by doing that, I get log of x plus 2 plus log of x minus 1 equals 1. And then I just apply the properties. The property says when you add logs, you can squish them together as long as you multiply the arguments. Now this is a type 3 problem. So to get rid of the log, we're going to exponentiate. Since it's a common log, we're going to exponentiate to base 10. And that gives us, these guys quasi-cancel out. I'm going to go ahead and do repeated distribution for this guy out at the same time. That's going to give us x squared plus x minus 2 equals, and then you should be able to figure this out. 10 to the 1 is just 10. Hey, it's a regular quadratic equation, so let's go ahead and solve it. Get 0 on one side. And man, someone is looking out for us. Every single example we've done is factorable. Who would have guessed? So that's going to be what? Plus 4 minus 3. So we get x equals negative 4 and x equals 3. But as always, you must check your answers against the original arguments. Let me just fast forward through it. If you plug and chug and check, negative 4 will not work, but 3 will. So if you think you're all set, that is it. That is solving log equations. I'm just going to do one more just because I want to do 2 examples of each. So if you're all set, feel free to exit the video. Otherwise, stick around. Let's go ahead and solve one more example. So suppose I asked you to solve log base 3 of x plus 15 minus log base 3 of x minus 1 equals 2. So that's the only difference. What if you had a minus problem instead of a plus problem? Well, the property says when you're subtracting logs, you can squish them together with division. That's the only difference. But everything else is the same. Hey, now it's a type 3 problem, so we can exponentiate. Since this is a base 3, I'm going to exponentiate with a base 3. So on the left, they quasi-cancel. So we get x plus 15 over x minus 1 equals, you can figure this out, 3 squared is 9. And we just have to remember how to solve rational equations. The idea is to clear the fraction, multiply both sides by the LCD, but we only have one denominator here, so that's pretty simple. We're going to multiply both sides by x minus 1. So these guys are gone. That gives us x plus 15 equals distribute 9x minus 9, and then hopefully for everyone it becomes a nice easy regular equation to solve. Let's subtract both sides by x. Let's add both sides by 9. So that's what 24 equals 8x and x equals 3. Of course, you always have to check against the original argument. Plug in a 3 for both of them. They are good, and that is your answer. So that's it. That's the second half of 4.5, using properties of logs, using exponentiation to solve log equations. So have at it.